So we're going to talk about the task queue API, what that is, the idea of tasks and webhooks. We're going to talk about push versus pull and performance. We're going to talk about idempotent queues and throttling, and some of the advanced features like task names and ETA. And then through this talk, I'm also going to show you 3 concrete examples of doing offline work with the task queue API. Including sending email, migrating a schema, and something called the write behind cache, which is really cool. And then finally, we'll talk about the future direction of where we're going next, more concretely. So for starters, let's talk about the motivation of offline work and what offline work actually means. So when I say offline processing, that's in contrast to online processing, otherwise known as background processing. It means that there's not a person there waiting for the response. It's something that just happens in the background when no one's around. Some kind of, report generation or data analysis or any kind of computation you want to do that has nothing to do with the user request directly. So App Engine is great for building web apps, specifically request-based, database-backed web applications. And we've heard over and over again from our users that they want to be able to do background work and batch processing. So a while ago, we launched the ability to run cron jobs, but this really isn't enough. It lets you do small amounts of cleanup here and there and work ever so often, but the finest granularity of execution is about a minute. So it's really not a high throughput system. And we'd really like to enable background processing in App Engine because it would enable a whole range of new applications to be built using this platform that never were possible before. And like I was saying, why do you even want to do background processing? Well, maybe you want to continuously do work. Maybe you want to incrementally process some data, compute some results. You can also use the task queue to smooth out load patterns and to reduce user latency. And generally, this is just a new style of computation for App Engine that we're providing. So it's new territory. Up until now, we've really been request-oriented, and now we're getting towards real computation. All right, so let's get into what is the task queue API and how does it work. So our first attempt at offline processing, we're delivering through something called the task queue abstraction, the task queue API. The task queue API is part of App Engine Labs. So App Engine Labs is a subset of our APIs that are still under development, still somewhat experimental. That means that the APIs may change a little bit before we say that they're fully released, although we're going to try our hardest not to break anything. It also means that we don't necessarily know how we're going to build yet so that people can grow this usage as much as they want, although we want to make sure that everyone can grow. So we're still figuring out the specifics of billing model and how to scale it out. And so the task queue is available for everyone today. There's a Python API and a Java API. We have integration with the admin console available. Free apps are allowed to do 10,000 tasks or 100,000 tasks a day, and build apps can do 1 million. And you can do a max execution rate of about 20 per second. And so that's all available to you right now if you sign up for an App Engine application, which is free. So let's talk about what you can actually do with that. OK, so what's a task queue? So many of you have probably already heard of this abstraction before. But it's a simple idea. You describe the work you want to do now, say in response to a user request. And then you save the description somewhere that you just created. And then later on, you have something come by and execute that work. So take the description and do something meaningful with it. And generally, with a queue, the reason it's called a queue is because it's a FIFO queue, first in, first out, which means that work is executed in the order it's received. And the other thing that's important is that all work is eventually completed. So if for whatever reason the execution fails, it'll be retried until it's successful, or you delete it. So the smallest example of task queue in action here is task queue.add and then description of work, whatever that may be. That would be the simplest idea. Just do this later. Add this to the list. So we'll get into what that description of work is in a minute. But let's just talk about some of the benefits of this approach. The first one is that this is asynchronous. Why do work now when I can do it later? Latency is a very important thing to a lot of application developers. So if you're using a task queue API, then in response to a user taking an action, say, send me a PDF file or a document describing this report or something like that, you can immediately return back to the user, OK, I'll send it to you. And they don't have to wait. There's no long spinning cursor or something like that. So you can decouple user latency from processing latency. You can also, and so on top of that, writing to a new task is actually cheaper than writing to the normal data store on App Engine. It can be around 3 times faster than the normal data store, which is really, really fast. So that's great too. If you know that you have a really high throughput, low latency need, then the task queue is a great way to achieve that. And it's reliable. Once you write a task, it will eventually complete. So you're guaranteed that kind of finishing. And it's also scalable. So storing new tasks, there's no contention on that. You can parallelize the workers that actually execute the work. You can parallelize the insertion of the tasks. So you can do a massive amount of work all at the same time and not be constrained by any kind of weird scaling factors. And then there's a lot of things you can do on top of this that we can get into later. Now, historically, the idea of a task queue is pretty old. Unix had 2 commands, at and batch, which people use still to this day. More often, you see people use something that, I've heard called like a poor man's queue. And it's essentially cron jobs and flat files. Every time they want to do something, they append to a file. And then every 10 or 15 minutes, a cron job will turn on and chunk through the file and do everything and then delete the file. So that's when people talk about asynchronous processing, that's a lot of the time what they think is the entirety of it. But that has a lot of problems. And there's a lot of kind of reliability issues. The cron job's only running on one machine. It only runs once every 15 minutes. What if it fails? Who do you tell when it breaks? What's the monitoring and alerting aspects of it? So having a cron job run on a single machine really isn't scalable in the way that we want this to work. Additionally, in the modern age, there are a lot of other task queue-like systems out there. So there's all the StarMQ systems like ActiveMQ, WebSphere-MQ, Tibco. There's Amazon Simple Queue Service. There's Azure queues from Microsoft. There's Perl and Python packages like the Schwartz and Twisted, Starling, which is popular in the Ruby world, BeanstalkD, and the list just keeps going. A ton of these things. And the thing is about queuing is that it's often conflated with pub/sub messaging. So people are like, oh, I need to do a queue. I'll just use this pub/sub tool instead. And I think that people don't realize what they're doing is using the wrong component for the task. And a publish-subscribe mechanism often will be able to do the work of a task queue, but you can actually do a lot better with a task queue abstraction directly. And the reason is that queuing systems are designed to maximize the throughput of data. That's what they're for. And great examples of queuing systems are like routers. They're just moving data around, handling queues of in and out. Data pipelines, just generally, any kind of data pipeline that companies have for financial data or mapping data, or like Google with the search data, it's all data pipelines. And the point of data pipelines and queuing systems is to fully saturate the network, disk, or CPU throughput of a machine. Now, publish-subscribe systems also maximize something, but they maximize transactions and decoupling. So in a pub/sub system, you're going for more transactions per second, say financial transactions or two-phase commit transactions, which have other kind of semantic guarantees, but they're not necessarily raw throughput numbers. So you might be able to do 1,000 bank transactions per second using a pub/sub system, but that doesn't necessarily saturate the network or disk of the machine. The other thing about pub/sub systems is that a lot of the time they're meant for one-to-many fan-out. So for instance, you'll publish a message that a new customer joined the company, and then, or a new employee joined the company, and then a bunch of subscribers will say, okay, give them payroll and give them, a parking spot, or give them, a bus pass, or whatever it is. You have a bunch of other systems that subscribe to it. So there's a decoupling between the publisher and the subscriber. And then there's other things that's really important in systems like that, like guaranteed ordering. So we're not doing any of that. We're doing a queuing system. That's what we're doing. We're trying to maximize the throughput of a data pipeline. And there's a lot of very useful things you can do with that. So as I'm explaining what we're doing here, just make sure that you make the distinction between a pub/sub system and a queuing system. So traditionally, this is kind of an example of how a queue system works. You have a queue at the top with newer tasks being appended to the end. You have a queue mediator somewhere in there. That could be another server, a set of servers, a database master, but it's some kind of mediating agent. And then you have a series of workers. And the workers are what are processing the queue. So every time a worker is free, it'll poll the queue mediator and it'll say, hey, I am free, please give me some work. The mediator will pop the head off the queue and then give it to the worker. The worker then commences and does the work, and so on. And so the workers are they're always running, even if they're not doing anything. And they're constantly polling the queue, even if the queue is empty. And this is basically state of the art for most queues and queuing systems. But this has a huge number of problems. First of all, the worker is just sitting there doing nothing most of the time. It's not event driven, so it's wasting work. If you're doing polling, you're constantly asking if there's something new, and there's nothing new, so you don't do anything. But then you stay resident. So the process is running, you're using memory, you have bandwidth overhead of polling, and that's just all waste. On top of that, you have a fixed number of workers. So in good time, like sometimes your workers are totally idle, and then maybe you have a big rush and you're processing orders or something for some holiday season. Then you'd have a huge number of orders come in, so then the admin would have to come in and say, oh man, we need 10 more workers, and has to manually bring them up. So so the administration burden of a polling system is very high because it requires manual intervention. Now there are ways to add smarter systems for doing this provisioning for you, but you have to build that, and most of the queuing systems on the market don't do that for you. The other thing is that with this kind of polling system, there's a limited amount of optimization that's possible. Many systems will fake polling with an actual event-driven system. Under the hood of TIBCO and a lot of these other ones, they're actually doing event-driven style messaging, but the worker is still hanging around. And so there's still that waste. They also use long-lived hanging connections between the worker and the mediator. So these poll lines, those are usually long-lived. So you can get some efficiency, but really not that much more than the general model. So how are we different? Well, the big thing is that we're not polling, we're pushing. We push tasks to your app so that you don't actually have to poll for them. And so the reason that's different is that we're actually using something called webhooks to do this. So a webhook is a HTTP request, and it's a RESTful push-based interface for work. And I'll kind of get into what that means in a sec. But many of our APIs are using this style. You've probably seen our XMPP API, our email receiving API. They're all webhooks, where we will translate some event on the system and turn it into an HTTP request. So recently, we added an XMPP API for Jabber messages. And every time you get a Jabber message, it's a post to your app. Every time you get an email, we have receive email now, it's a HTTP post to your app with the body of the email. And our task queue API works exactly the same way. Every time a task executes, we send you a request with the description of the work. So tasks is webhooks. What does that mean? So a task is just an HTTP request that you define. You say what the URL is, the method, the body, any headers you want to have on it, like a full description of that HTTP request. You enqueue it using the task queue add method I showed you, and then we'll execute it for you later. And if you return a 200 or 2xx HTTP response, then the task is done and we give up on it. Otherwise, we'll do exponential backoff and retry the task until it's successful. So that's the big difference. We're converting tasks into HTTP requests, which is a very familiar interface for App Engine developers and web developers in general. So let me give you a really quick concrete example. This is one of the simplest things you can do. So this is a mail sending queue. Maybe one of the reasons you'd want to do this is because you don't want to overwhelm someone's mail server by spamming it or overwhelming a partner site, or maybe you're trying to throttle certain users, whatever. So you would want to use a queue to do that. So also mail sending sometimes takes a long time. So here at the top I have a worker defined. This is an HTTP worker written in Python. It's just a request handler. It takes an HTTP post at the top. And in response to that post, it'll call send mail. part of our mail API. And it says the from address, which is me, and then the person to send it to, the subject of the mail, and the body. That's it. So that's all. That's the whole description of the worker, using all the same APIs you're already used to, and the same interfaces through HTTP, but you're doing offline work. And then to actually execute this, I enqueue a task, and I say, OK, this is the URL of my worker, and these are the parameters that I want to have go into the mail message. That's it. It's really easy, right? It's like calling a function, but at an HTTP request level. So I can actually show this in action, if this works. Yeah, OK. So this is an amazing demo. I'm actually really proud of this one. Get ready. Hold on to your seats. Ha, OK. It sent an email, I swear. You can try it for yourself. It's taskqueueexamples.appspot.com. If I had my email loaded, you'd see it. But it's really quick. I can click this button all day long, and it's sending me mail. It'll send you mail if you log into it, so don't worry. You're not going to spam me. Anyway. Oh. OK, so that's kind of a contrived, stupid example. We'll get into a better one pretty soon. But let's talk a little bit about how this queue works. We're doing the opposite. We have the queue. Newer tasks are being added as normal. But instead of polling, we're pulling them off the head with a mediator. And then we push them to the request handler as need be, as new tasks come in. So that means that you don't have to have any workers around when there's no work to do. That means that your application is extremely lean. You're not wasting any CPU time when you're not doing work. What's even cooler is that we can scale you out when you need to do work. So App Engine, we do load balancing for you. We can pull up more threads for you whenever you need them. So whenever you have a bigger queue that has more work to do, we'll just spool up more threads and then handle the queue. So it's about as elastic as you can get at the request level, and you can handle a huge amount of throughput on this. And right now we're limiting the throughput because of the labs release, but our plan is to make it very, very high. So like I was saying, it works by adding threads depending on your workload. The maximum number of threads you get depends on the throughput of your workload. So for instance, if you have very low latency tasks, then you'll get a lot of threads. Well, like I was saying, we have a lower limit right now because of our labs period, but as soon as we get rid of our labs period, we're going to have a very high maximum rate limit that will just be in place for safety. And the other thing that's great about this is because workers are just described as request handlers, you get all the great things from App Engine you're already used to. So you get integration into the admin console as normal requests. You get application and request logs that are searchable. You get dashboard statistics and all the graphs that go with it. So I can show this too. Where's my mouse? So here's the dashboard of my task queue examples app. And so you can see a couple of spikes of work I've had here and there. And down at the bottom, you can probably read this OK. You can see I have a few calls to counters, a few calls to the migrator, the right behind cache, and the mail handler. And I'm still, I'll get to these examples later, but these are the same kind of tools I already have at my disposal as an App Engine developer that I'm reusing for offline work. So here I see the worker email. I can click on that. And then it'll take me to the request logs, and I can actually look at the request logs, and it can tell me, oh yeah, here's the person they accessed it at this time, and I can look at the refer, and I can do regex scans, and all that great stuff. I guess while I'm here, I'll also show you that we have, as of the most recent release, 127, we actually let you look and introspect your queues. So we have all the queues listed here. And I have nothing in the queue right now, but you can actually look at the tasks in the queue, see if they've failed, see how many times they've retried, delete them, and flush the queues too. So you can do all kinds of queue management now that you couldn't do before. Cool. OK, so let's get into some details. OK, so this is where it gets a little more advanced about the semantics of these tasks, and this is where it gets really interesting, I think. So first of all, with the task queue abstraction, idempotence is really important. What is idempotence? That's like a $50 word. So idempotence means that it's a math term, right? And it means that when you do something, if you do it again, it has no effect. Okay? So it's like multiplying by 1 is the ultimate idempotent operation, but the idea is that if you're implementing a task worker, you want to try your hardest to make the work idempotent, so that if the task happens to run a second time, that you properly deal with that, or you don't care. So in my email example, well, if I send 2 emails, it's not the end of the world. It doesn't need to be idempotent. But in other things like a schema migration or some other kind of very sensitive data manipulation, I'd want to make sure that the manipulation didn't ever get repeated. So then I have to add some stuff to my code to ensure that it's idempotent, that it withstands repeated attempts. And this is necessary because a failure can happen at any time. When you're running at scale, nodes drop out and requests stall and things happen. And so you need to be able to deal with those properly. And so this is the best practice of dealing with a task queue system. And this is not only an App Engine thing. This is any kind of task queue system running at scale has this constraint. Right. And so the other thing is that, like I was saying, tasks will be retried until they're successful. But it is possible for tasks to run twice, even without server failures. There are certain race conditions in certain kind of eventually consistent edge case, eventually consistent edge cases that can cause a task to run twice. So you need to be responsible for this as an application developer and think about what the work you're doing is. Make sure you plan accordingly so that you're not burned by this constraint. And this single constraint is what gives the task queue all of its throughput, its flexibility, its scale, its parallelization. All those great things come from this. OK, so the other thing is that you can, when you're working with queues, you can define multiple queues. And the question is, what are the queues for? Because you define the work as a URL. This is my worker on this URL. So we have workers, we have tasks that describe the work. We have workers that are just URL handlers. And then we have queues also. So a queue, every task goes on a single queue. An application could have multiple queues. And the reason you want to have multiple queues is for isolation. Queues, all they do is define the execution order of the tasks. So new tasks come in on this side of the queue and they go out on this side of the queue. And by doing that, you have isolation between the different queues. So if you have a queue that slows down because of some slow or bad tasks at the beginning of the queue, that will affect the other tasks in that queue. So you can use multiple queues to isolate the tasks from each other so that certain kinds of work, say high priority work, will run faster or run without interruption or whatever. You can also throttle each queue. So for instance, this is a queue YAML file. There's something like this for a Java XML file too. And you define your queues and you define the rate of execution. So you might want a really fast queue. And you might really want slow queues too. And the reason is that maybe you want to combine work periodically. Maybe you want to, every 5 minutes or so, take a batch of work all together and then do one database write or one kind of computation. Maybe you want to ensure the stability of your workload so that you don't burn more than $1 per second of CPU time. Another way to use this is that the data store is limited in its write throughput per node. So maybe you want to smooth out the load pattern of your database writes by using the task queue. You can do that now. You can also, you might have certain agreements with other sites sending them HTTP requests or XMPP messages or emails where you can't exceed 50 per second. So this can be used to enforce that kind of policy. And like I was saying, it lets you prioritize work. So the queues are isolated from each other, so you can have a fast queue, a slow queue, a reliable queue, and a flaky queue, and use them all differently. And the kind of advanced thing here that's hard to understand sometimes is this weirdo diagram. So you have the tasks described on the left, which have URLs and data encoded. They describe the work. On the right-hand side, you have the URL handlers for those tasks, which are standard request handlers that you write as an App Engine app developer. And then in the queue, you set up the various prioritization and isolation. So you can actually have a many-to-many relationship of tasks to queues to workers. So it's really a third dimension of configuration. It's something that you kind of have to think about a little bit before you understand how it's useful. But it is very useful for ensuring a quality of service with a task queue. Cool, so let me get into some more examples. So another concrete example is schema migration. People have data in format A and they want to change it to format B. Now, without the task queue API, there were two options for doing this on App Engine. The first was setting up a cron job that would go through the entities and slowly migrate them. And maybe it would keep something in memcache, like a cursor in memcache or in the data store. You could also do this, drive this from an HTTP or HTML page itself, which is really awful, but you can do it. The other alternative is to use the remote API or the bulk loader to actually dump the data set and then reformat it locally and re-upload it, which is a lot better now that the bulk loader is getting better and better by the day, but it's still not really a migration then. It's a re-uploading, right? So you really want to be able to do a schema migration as the site serves, which is pretty important. So with the task queue API, this is really easy to do. You define a handler that will get the next n entities. It will modify them to the new schema. And it'll do a batch update of all those entities. And then it'll enqueue a task to resume starting after the current position. So like continuation passing style. And if this fails at any time, the task will retry. So you're guaranteed it's going to get through everything. And that it will end. And you can actually guarantee some idempotence here as well. You can make sure that each item only ever gets migrated once. So that would be the idempotence guarantee. So how does this work? Let me show you. So let's say I have two kinds in the data store. Again, this is Python. These are model classes as part of the App Engine ORM. I have the first user kind at the top, which has a name all as one string. Then I have the second user kind that has a name split into first and last names. Then I have two silly little conversion functions that converts between the two of them. So one of them splits on a space and makes a second user kind. The other one takes the first and last and concatenates them with a space. Okay, really simple. So that's the only difference, is that the space, right? Okay, we got it. All right, I'll go slower now. So this is my request handler. At the top, I do a query. The from kind being either the first model, so the first user kind, second user kind. Those are my two, so I'm gonna say first and second. So I do a query for the kind I'm trying to migrate from. And I say, if I'm starting off, if I have an offset position, I'll get back to this, the if start, I'll get back to. So let's just go down a little bit and say old. So these are my old entities in the old format. I do a fetch of 10 of them. If there's nothing left, then I'm done. Otherwise, I calculate the next bit of work after this first 10, like the last one. I get the key of the last one, so I can start after it. Then I migrate each one to the new schema, creating a new list. Then I put all of the new ones, and I delete the old ones. And then once I've done that, I add a task to begin the same work. But here you see how start says next start. So I use the key of the last position. This is at the very bottom. I use the key of the last position to say where my next starting position is as an offset. So then going back up to the top, where under query it says if start, then add a filter. All that's doing is letting me page through the data, doing offsets in an array, basically. And so there are many things you can add to this to make it more transactionally guaranteed. I'm just trying to simply show you an example of how this would work. But as you can see, it just kind of keeps a cursor and it goes through, and it adds new tasks every time it makes forward progress. There are many things you can do also to parallelize this so that you do most of the migration in parallel as opposed to one chunk at a time. But it's the same idea. You can go through your work in parallel, or you can go through your work in one task at a time and migrate your data. So I can show this in action. All right, this one's a more interesting demo. So here I have a bunch of names, random people who I've given this talk in front of. I think once before they typed in their names, so sorry if there's some inappropriate names in there. And I have the first kind names at the top. These are ones with the spaces in them. And then you can see at the bottom I have no second kind names. And then I can choose to do a migration from the first kind to the second kind. So migrate first to second. So then I click the migrate button, and you'll see how the second names are getting populated. And if I reload again, they're all second kind names. And I can go back the other way too. I can do second to first, and I push the button, and you'll see first names show up, and they're chunking through. Maybe I hit a little error. So you'll see though it'll retry. We'll wait for it, but it'll eventually retry and finish everything. So what's interesting about this is, if you notice when I click the migrate button, the results already started showing up before I even reloaded the page. Like it was halfway migrated before it was even done. So there it finished. So that's a great example of task queue finishing. I probably hit some kind of latency error because I haven't used this app in a long time. But what I was saying is that when I clicked the migrate button, the page reloaded, and some of the names had moved from the top column to the bottom column or whatever. And what is that? There's no like smoke or mirrors here. What it is that as soon as you add a task, we actually have a fast path, and the task will start to execute. So that means if you have 2 timelines of tasks executing, as soon as you add one, it will actually start to run reentrant at the same time as your original requests. So you can get huge amounts of throughput in this way, because adding a task was actually kind of like calling yourself and spawning a thread. And if you look in the request logs, which I have here, you can see that, where is it? Right, okay, so here I have, I was trying to figure out a good example. These are all the same, okay. What happens is that I have requests here, names, which was, one of these is a post. And what happens is that, sorry, this is what I want right here. Okay, so here's a post to start the migration. And it came in at 8:02 a.m. Pacific time and 37 seconds, 0.9, okay? Now you'll see right above it is the actual migration task. And the migration task started at 37 seconds, 0.96. So within 10 milliseconds, the task had been added and it already started executing. And you'll actually often see situations where the first task will complete fully before the other request has even finished. So you can get multiple threads of execution at the same time, which is really great. I meant to zoom this in, sorry. So yeah, so you can see the times here. It's, it's within 10, 20 milliseconds, so it's pretty good. Okay, so let's get into a few more details. So we talked about idempotence as a feature of the task queue. Another thing that we have in the task queue API is the concept of an ETA, estimated time of arrival. So what is this? It's basically saying when the task should run. You're scheduling the task for some time in the future. It's very much like the @ command in Unix. Now, this is very different than visibility timeouts. If you've ever used Amazon Simple Queuing Service or Azure Queues, they have visibility timeouts, which is kind of like a lock that a worker has on a task. This is nothing like that. The ETA is specifically a time to run the task. So it's useful for doing fine-grained work in the future when you know, okay, I need to do this work 25 seconds from now. I need an alarm clock to go off or whatever. So an ETA can be used for that. You can also do prioritization with an ETA. So you can say, oh man, this task is useful, but I really probably don't need to do it for 15 minutes. So just, and I'm pretty loaded right now, so just schedule it for 15 minutes in the future. If you don't want to clog up your queue, you can do that. You can also use cron and task queue ETAs in combination. So you can do periodic cache clearing and cache refilling. You can flush buffers, you can report incremental results, and like I was saying, you can do prioritization with ETAs. So they're a very useful tool for kind of controlling fine-grained execution of your tasks. The other thing that tasks have are names. And this goes back to the idempotence specifically. So if you want, when you enqueue a task, you can give it a name. If you don't give it a name, it'll have an auto-generated ID. But what's interesting is that after a task with a name is done running, if you add other tasks with that same name, they won't run. So this is how you get kind of only once semantics with the task queue. You define the task name, you add it, and then any other attempts to run that task again will never happen. And the first one that was added will win the race, basically. And so this can be used for enforcing only one semantics. And this is how you can make sure that you only migrate a schema once and only once. So you click the migrate button, that enqueues a task with a very particular name. And so if you click that migrate button again, or accidentally click it twice, or the request comes through twice, the task add will be the same name, and so you'll dedupe that re-add. So you have a high level of confidence in the kind of only once. Now note that this is different than the chance of multiple execution. So that named task may run more than once. It's possible in an air condition. But basically, task names let you control the starting point and say that this task with this name at this starting point of some chain of work will only be enqueued a single time. Cool. Okay, so now let's get into the next example. This one's, I think, the coolest example, and this is the one that's most useful to developers immediately. Something called a write behind cache. So you probably will recognize this even though you haven't heard it called by this name. It's a very common practice that a lot of web developers use to scale their sites. So the idea of a write behind cache is to minimize writes to a database with periodic flushing of a cache. So the idea is that every time you want to write some data to the database, you put it in a cache instead, something like memcache. And then periodically, every minute or every 10 seconds or whatever, you pull the data out of the cache and submit it to the database. Now, what's amazing about that is that it decouples your traffic from your write throughput. So I don't know if you've ever been writing an App Engine app and had contention on an entity or on a MySQL database, you have a hot row or hot table. This is what happens when sites scale. A write behind cache will actually let you turn that off, so you have a controllable knob and say, you know what, my database cannot go faster than 10 writes per second, so I'm going to control and just say 10 writes per second. So before, you might have done 100 writes to the database or data store per second, and now you can say, okay, it's only going to happen once, and I'll write the rest to cache. The trade-off, because nothing is free, the trade-off is that there's a small window of time where you might lose data. But for most sites making this trade-off, that's okay. And that time window can be very small. It can be on the order of milliseconds if you want it to be. It's really up to you and what you're trying to tune. But let me get more into this so you can understand. So this is my giant diagram. So UML fans in the house? No? Okay. So the smiley face is a user using a web browser. They send a request to my request handler, which, let's say this is doing pokes or votes or something that's a very high throughput activity. That request will then do a write to the cache saying that the user action has happened. The user will then optionally add a task to the queue, which is a very high throughput, parallelizable, low latency action. Then sometime in the future, the task will wake up and the task will invoke itself, essentially, and run another handler. And the handler will then do a periodic read from the cache and then do a batch write to the data store. Time going down here. So this is the decoupling between user action and data store writes. And this is what basically every site on the net that has appreciable size, this is what they're doing under the covers to make their site scale cheaply. And here's your failure window. If your cache gets evicted during this time period, then you lose your data. So you need to tune that based on your particular constraints. It's really up to you. It can be, but like I said, it can be as little as 50 milliseconds, 100 milliseconds. And you can add plenty of things in your user code, especially if you have like an Ajax-y kind of UI, to confirm that the write went through within some time window. So you'll be like, oh, write this to the data store, but put it in the cache first, and then 10 seconds later, double check to make sure it's there. And if it's not, then deal with it. So you this kind of two-pronged approach for reliability with the client side works really well for when you have a smarter browser. So the next example I have, I have a concrete example of this, which is a hit counter, basically. I want to, people have already wanted this on App Engine for doing analytics and stuff like that. They want to know how many hits they have for a certain page. App Engine is not the best suited for doing counters, so we've had a series of ways of explaining to people to shard their counters, to do this on App Engine. That works pretty well, but it's relatively expensive. You're still doing a lot of data store writes. And you really have no control over write throughput. So if your traffic goes through the roof and you don't have enough database shards or counter shards set up, you still have a problem. Now, if we're doing a page hit counter with the task queue API, this gets really easy. Every time there's a hit, you increment a counter with memcache. And then you enqueue a task, and that task will copy the values from the memcache to the data store. And then you use the queue throttle. Remember we talked about queue throttling before. Use that throttle to limit the maximum writes per second to that entity group in the data store. So I can tune that to 1 per second or 5 per second depending on the shape of your data. And then later on I can read the updated value either from the data store or from memcache to get the most recent value. They should be relatively in sync. So that's kind of the full picture. Theoretically of what we're doing. So here's the code. So this is the first part. This is the part handling the user requests. So at the top we have our counter entity. This is the ORM model kind. It has a count. That's it. And then it has a key name. So that'll be the name of it. We'll give it a key name, the primary key. So when the post comes in, we get the key name. We do an increment, a memcache increment, and say, hey, if it's in there, increment it by 1. If not, then give it an initial value of 1. So there's a nice default in memcache now. And then once we've done that, we try to add a memcache. We try to do a memcache add of a key. And if the memcache add returns true, basically saying that we got to add the task, then that means that this is a dirty bit, which basically means there are no tasks already that are trying to do this work. Okay? So this is like a flag. It's a dirty bit saying, okay, yep, I need to run a task. I need to do this. So then the add, which is great about, the thing that's great about a memcache add is that it's a speculative lock. So it's like a mutex. So when you add, you kind of have a lock until that item is deleted. So we grab a lock there, and once we have the lock, then we add the task queue task. And again, with a simple description of the worker to point at, and then the key to do the flushing, right? So that's all there is to it. So then on the worker side, we'll get this post from the task queue. We pull out the key. Then we delete the dirty bit, because we assume that it's in there for memcache. We delete it. Then we get the value from memcache, and if the value is actually there, if it's not there, we'll log an error, and if it is there, we'll create the counter and then put it into the data store, overwriting whatever was there. We don't really care. We don't have to do a get. We just blindly put over the old one. So that's it. I've now decoupled my hit count throughput from my data store throughput, and this counter can scale ridiculously well, basically as much as you want to throw at it, and really cheaply. Like you don't have to spend much CPU at all. So it's great, and you can do a lot more than just counts with this. You can do a ton of stuff. So I have a demo, and this is another kind of spectacularly simple demo. So I have a series of named counters here, and I can type in one of their names, and it increments. Wow, Brett, I can do that. That's amazing. Yeah, I know. It's really easy to do that. It's a counter, but that's doing all the task queue machinery behind the scenes. And the task queue is so fast that it actually comes back and finishes before my browser has had a chance to go back to App Engine and reload the page. So you don't necessarily have to take my word for it. Let's see. So here you can see, so here's my post to the counters page at 352, okay? Then the task starts running at 10,383, so within 25 milliseconds-ish. And then my browser finally reloaded the page 100 and some odd, 200 milliseconds later on this request. So here's my get. So the task fully completed in 50 milliseconds between the time I clicked the button and the time my browser reloaded the page. So it's that fast. It's really, really fast, remarkably fast. Great, okay, so those are the concrete demos. It's taskqueueexamples.appspot.com. You can play around with it. I think the source code is linked off of somewhere. It might be on our App Engine site, I think now. It's in our Google Code site for our App Engine project. You can download the code for all that stuff. So if you want to play around with it, you can. So last, just to wrap up, let's talk about the future. So we've got more API features on the way, queue management, flushing queues, controlling the rates of queues during execution time programmatically as opposed to a config file. We've talked about the notification of queue events, like tell me when a queue is empty, tell me when a certain number of tasks have finished running in a queue, something like that. We also want to have the ability to do batch addition of multiple tasks at once. So that's like fan out. And we also want to have fan in, so we can take 50 tasks that were all in queued and then execute them all at the same time, which is really important for kind of maximizing your throughput. So yeah, so batch processing, for now the task API is really good for small data sets, something around 100,000 rows. It's great. But we really need more tools for parallelization and high throughput and processing data store entities in mass. We need better features for aggregation and statistics and logging and monitoring and on and on and on to really get up to mega data sizes. And so eventually we'd like to support a MapReduce-like abstraction. And to do that, we're going to need an intermediate storage facility. We're going to need to have a reducing sorter, a bunch of other kind of pieces that are missing right now. And the other thing is that we want our MapReduce to work with both small data sizes, like 50,000 entities, to data sets well over a terabyte. We also want to have things that help with workflow pipelines and stream processing, which are all great fits for the TaskQueue API. Right, and so that's stuff we're going to be working towards and getting on the roadmap as soon as we figure out where it's going to fit in. But that's something we're actively working towards. So to wrap up, use the TaskQueue API, make your existing app faster with lower latency, scale your app and reduce costs at the same time. Amazing. Add new functionality you thought you couldn't do before because you can finally do background work. And take advantage of webhooks for easy debugging. They're just requests and responses. So if you want to test out a task, you can send a request at it yourself. You don't even need the queue. You can debug. You can take the payload and debug the queue yourself. So it's great, a really useful model. Right, and that's it. So any questions of any sort? I don't know if we have a mic or anything, but you can just yell. Yep.
Yeah, I would like to ask a question about the memcache behavior. Is it going automatically on the background when your App Store application runs? Because looking at the statistics of my application, I've had about 70,000 requests and about 60,000 memcache API calls. But I haven't used any JCache API in my application.
You haven't noticed any what in your?
Okay, I haven't used any JCache API in my application.
Okay.
But still in the quota list, the quota details, I can see about 60.
Okay, yeah, no, I think I understand your question. I'm not really sure. Maybe, let's talk after, because I'm not sure what that specifically is. Yeah, sorry about that. Yeah. Yeah, yeah, I think I understand your question. So the question is, hey, these worker URLs are sensitive. They're public URLs. We don't want anyone to hit them. What do we do about that? So if you've used an app YAML configuration for App Engine or a App Engine web XML file to set up your URL patterns for your app, in there you can specify that the login is restricted to a user or to an administrator. And the secret sauce here is that task queues can bypass that check. So a task running can hit a admin URL that's locked down for only admin access. So the best practice for securing workers is to make them admin-only URLs. So then if you want to, you can debug a task by sending requests manually to it, and you make sure that the rest of the world can't access it. That's the best practice. So other people, though, they may want their workers to actually emulate a user-received request, and so making those URLs public is useful sometimes. But yes, the best practice is to lock down your workers and make them admin-only URLs. That's a good question. Any others? OK. Well, thanks a lot for coming, and I'll be here if you have any other questions.